Hi friends, welcome to my YouTube channel. This is first part of lecture number 2, and in this lecture we will study core and windings of transformer. So core is very important part of transformer. Windings are wound on core. Primary and secondary windings are linked inductively, or we can say magnetically, with the help of core because core carries the useful flux. We have to take care of some very important points while designing a core. So what are these important considerations? First is maximum flux density. Second is minimum losses. It means while designing the core, eddy current loss and hysteresis losses must be minimum. Third important point is economy. Economy means we have to limit the cost of core. And fourth point is reliability. And last point is low level of noise. Now I tell you about the core material. So core of transformer is made up of CRGOS. CRGOS. CRGOS means cold rolled grain oriented silicon steel. CRGOS is made by silicon alloyed with low carbon content steel and cold rolled. It has low hysteresis losses, high permeability, and low reluctance. Maximum flux density of cargo is nearly 1.9 Tesla. After this core gets saturated, cores are made up of laminations to reduce eddy current loss. Now we will derive a very important derivation that is associated with the design of transformer. We know that EMF equation of transformer is E is equals to 4.44 BMF divided by area A. Here in this equation, E is the EMF per turn, Bm is the maximum flux density, F is the frequency, and A is the area of core. So we can write area of core as pi d square by 4, where d is the dia of core. So on putting this area A in the equation of EMF, we get E is equals to 4.44 pi d square BMF divided by 4. So from this equation we can write two important relations. First is EMF per turn. E is directly proportional to the square of diameter, and second is EMF per turn is equals to V by N, where V is the applied voltage and N is the number of turns. From these two important relations we can make some very important point. See, if suppose if voltage is constant and if we increase the dia, then number of turns decreases. If number of turns decreases, then the height of core leg also decreases because less height of core leg is required to accommodate lesser number of turns. But core losses increases due to increase in dia and copper losses decreases. Why copper loss decreases? As number of tons of copper decreases, that's why copper losses decreases. Due to increase in dia, the weight of steel in the core also increases. So these are the important relation we can conclude from these two points. Okay. Now next is flux density can be controlled by area of cross section of core. Okay, because maximum flux density in the core is equals to the B upon A, phi upon A. Okay. Now next is concept of stepped core. So we know that primary and secondary windings are wound on core. If we make the core circular, then copper will be used, less copper will be used to make the given number of turns. Why it is so? This is because a circle has minimum periphery for a given area. Due to this, conductor material required reduced and IR square losses also get reduced. But problem is that a circular core requires a large number of laminations of different size. So for economic consideration, stepped core is used. So this is the diagram of a two-stepped core. Here in this two-stepped core, the laminations of two different sizes are used. So generally 2, 3, 4 or 6 stepped cores are used. So this is the concept of stepped core. We use stepped core to shape the copper material. Next is mitred joints. The lamination cut at 45 degrees, the limbs and yoke lamination edges placed at the mitred joints in a transformer core. It further minimizes the core losses. Oil ducts are used to cool the core. So this is all about the first part of lecture number 2. I hope you enjoyed this video. Thank you.